At 3:35 a.m. Pacific Time, satellites in the Navstar GPS constellation over the Eastern Hemisphere began transmitting a surprising event code. The Integrated Operational Nuclear Detonation System had detected a repeating double flash signal originating 1.4 kilometers above sea level over Inner Mongolia. This report comes as a shock to the public, but any kind of global military response is inexplicably muted. Nations remain silent and observe as over the course of an hour 80 Chinese astronauts reach and leave Earth orbit inside a 12,000-ton spacecraft on a cascade of 840 nuclear detonations. As the significance of the launch sets in, initially expected denouncements of the act never come, and instead, congratulatory diplomatic nods by world powers validate these events as pivotal human history. 6 hours before, the People's Republic of China's national press had circulated a government memo assuring an imminent peaceful launch of a nuclear pulse rocket. Initial response had been questioning and accusational, but the short notice of the announcement stifled any cohesive diplomatic response. Communiques made later that day stated the U.S. aims to actively cooperate with the new nuclear pulse program and presents a complete press release for a modernized Orion which will be launched from a soon-to-be-built launch site in Alaska. Statements arriving later throughout the year confirm that the Russian Federation will be assisting the U.S. nuclear pulse program, contributing fuel materials, subsystems, and cosmonauts. This rapid adoption of NPP by the world's powers does not go unnoticed. Nations begin contributing towards these programs as a means of gaining national prestige. Since there is a growing belief that most people on Earth could experience commercial interplanetary flight in their lifetime, the significance of the NPP programs gains overwhelming support. Frederick Strain, in his crucial book, Confronting Nuclear Addiction, describes the reasons nations pursue nuclear weapons. He emphasizes that a state might ascend or descend this hierarchy depending on ambitions, and that the relationship nations have with nuclear power are often reactionary and based on immediate state desires rather than national policies. He concludes that a nation's nuclear behavior may be approximated within a human psyche, even at a global level. This is illustrated by Strain's hierarchy, which by no coincidence closely resembles Maslow's hierarchy of needs, a methodology for assessing individual human behavior. There exists today two general schools of thought around the nuclear pulse drive. Being the first iteration of nuclear pulse propulsion, Orion is the most well-developed and still the most ideal for modern revival. Or, the nature of Orion's operation poses a security and proliferation risk, and thus while pulsed nuclear fission is not out of the question, the nature of self-actuating nuclear devices being produced and stored in large numbers is simply not justifiable within our modern anti-proliferation paradigm. We can observe that the reasons for not building Orion have remained virtually the same from 1963 to today. Nuclear technologies and the aspiration to create nuclear devices are still tied to national desires for power and linked to statehood, national status, and prestige. Considering these motivations, we can make qualitative assessments of various nations' ability to adopt nuclear rockets. As we witness the rise of several other states to participation in space with nuclear technology, notably India and China, we must evaluate their nuclear commitments in comparison to the United States. In economic terms, the United States' ability to foster its citizens' talents and energy is its main strength, but also defines our space policies. India has generally pursued this path as well, although their dedication to this economic stratagem has fluctuated. India and the United States are in similar positions in this regard. They rely on the decision-making of their industries, lobbies, and congressional bodies to enact new space programs. India probably has more freedom to independently pursue lofty NPP projects, not being subject to the same public optic concerns over large project spending. China is in an even stronger position to pursue Orion. The nation may execute tasks through its partial command economy and relies on military, industrial, and social projects to maintain cohesion of its industries. This environment is well suited for the deployment of NPP technology. Further, the nation has experimented in the last decade with breakthrough nuclear fusion, signaling a desire to master portable fusion for energy production. These nations are subject to international law and are bound by the Partial Test Ban Treaty and Outer Space Treaty. China was not signatory to the Partial Test Ban and only accepted the terms of the Outer Space Treaty retroactively. The language of this 1967 document specifically limits the use of weaponized devices. Any nation could use the argument that Orion functions on peaceful nuclear devices as a way to circumvent past treaties. US President Jimmy Carter set the precedent that attacks on US spacecraft or satellites represent an act of war, and we ought to assume that today any attempts to destroy a ground-launched Orion would not be a justified military action on this premise alone. In order for a modern Orion launch to manifest, we must address two major criticisms of the concept as it pertains to a ground launch. While we will discuss vehicles built in space, launching NPP craft from the ground was always the intention of Orion because this takes full advantage of the system's high payload capacity. Fallout or radionuclide production has been a persistent point of contention, and another is operational security of nuclear devices. Once these topics are treated, we'll return to a broader context of proliferation, which is the ultimate obstacle driving these rationales. There is a largely false notion that ground-based Orion launches will produce excessive radionuclides and other harmful radiation, leading to long-term environmental effects. When proper active and passive measures are taken, a single Orion launch produces negligible amounts of contamination. Ironically, the case can be made that a properly planned modern Orion launch would produce fewer carcinogens than a historical chemical rocket launch, and as fantastic as this sounds, it's been proven attainable using understood methods. We'll consider the process of changes occurring on the device mass from the moment it leaves the vehicle. Keep in mind, I will simplify this process for the sake of brevity, and I will not use the technical units. Assuming a device mass of 400 kilos, our fission tamper represents 9% of this, or 35 kilos. I am vastly overestimating the mass of the tamper for the sake of argument, so keep in mind this mass can be further reduced by up to 80%. While other parts of the device will produce radionuclides or fallout, most will be extremely short-lived. The leftover fission material and fission products of the nuclear material itself represents the most concerning contamination source. The fission reaction will generate dangerous products representing between 0.4 to 0.6% of the tamper mass, or 20 grams. 5% of these products are considered dangerous to biological life with either consumption or continual exposure. One bomblet with a 35 kilo tamper will produce less than 1 gram of harmful fallout. As the fission tamper detonates, this small amount of fallout material will interact with the fusion component. Dyson discussed various types of filler material to both arrest neutrons and reduce the activity of produced fallout. Boron and polyethylene were examined for this purpose, although today, better materials no doubt exist. The exact reductions will depend on the device's tonnage and type, but around 50 to 80% reduction of dangerous fallout can be assumed. At this point in the thought experiment, our device is completely detonated and the fusion cascade has burned out. Alpha particles and gamma radiation are dispersed in a deflected cone towards the ground, becoming highly dispersed once the vehicle reaches about a kilometer in altitude. Assuming the launch does not kick up any dust, there are no more radionuclide sources beyond the device. The dangerous fallout which was produced by one device consists of about 0.5 grams of radioactive isotopes spread out over the launch area, and these products will remain dangerous to humans for a short time. Depending on the materials used, this mass can be reduced by over half via chemical and nuclear interactions. These products are only harmful to humans if directly consumed or absorbed by the body, and most of them will decay in the hours and days following. The primary concern here is that this material does not reach open drinking water sources or crop fields. Consider the statistic produced by Dyson using a general atomic study on the cancer rate resulting from the original Orion proposal using pure fission devices of about 50 to 70% efficiency. He claimed 1 death by cancer per year from a single launch. This was without any of the possible reduction methods discussed, and modern thermonuclear devices will operate at around 98 to 99% efficiency in comparison. Electron activation will result from ground NPP launches. Nuclear detonations in the low atmosphere can create unnatural belts of radiation, and this electron activation problem was resolved during Orion's planning. It was found that launching sufficiently far from the equator would reduce electron activation greatly. So long as launches are intermittent, activation times are extremely low, and activation will return to normal levels within minutes to days. By launching the craft in the ocean, the chemical properties of water vastly reduce the production of fallout at low level. Since produced radiation must interact with dust or other aerosolized particles to produce harmful fallout, the marine environment is an ideal location to minimize this creation. Water also blocks alpha, X-ray, and gamma radiation, meaning harm to marine life is minimal. Deuterium aerosol can be produced in a tall plume over the launch site to minimize radiation at ground level. This heavy water fog can be vented by the craft as well, reducing the spread of radiation at higher altitudes. Larger vehicles use nuclear mass more efficiently, meaning the amount of produced fallout will only slightly increase as vehicles become larger. This means larger launch vehicles are inherently preferred if contamination is to be minimized. NPP launches pose a potential threat to modern satellite constellations, which increase in density annually. The electromagnetic pulses generated by the craft might do damage to nearby satellites, and solutions to this problem include using lower-yield devices more frequently to pass through risky areas in low Earth orbit. When NPP ground launches occur, global cooperation will be needed for operational safety. United States-based NPP vehicles would realistically be deployed under United States Air and Navy or Space Force under a joint command managing logistics, manufacturing chains, monitoring, and the launch installations used. This reality also simplifies many aspects of reviving the Orion program today. The Air Force still has access to all of the program's resources as it did in 1965. The policy questions of using nuclear pulse propulsion are also simplified by employing these military channels, since the Air Force already handles nuclear devices. The United States Navy will also provide the logistical support needed to accomplish a sea launch. Security and proliferation are logical concerns given the element of uncertainty surrounding Orion, but I do believe that the precedent for this is already being set by our paradigm of storing dozens or hundreds of warheads aboard single submarines, a practice several nations actively engage in. NPP rockets should be subject to increased levels of military protection due to their cost, and whenever it becomes possible, nuclear devices should be manufactured in space due to much higher security and the reduced cost of manufacturing and nuclear reprocessing in microgravity. Proliferation in space does not yet have a valid paradigm, so the future of these activities for peaceful purposes seems secure. The political situation for NPP is realistically more salvageable than many believe, especially if a major impetus existed. The long-term benefits of NPP beyond Earth appear irrefutable. But the NPP concept has not always been popular to taxpayers, so the risk of reviving these programs is notable. There are numerous addressable instances in historical documents where AEC has been recorded falsifying the work of the US science community, such as in the case of Project Chariot. This was an experiment to use nuclear devices to excavate an artificial harbor in Alaska. The project was misguided from the start, being described as an economic development effort under Project Plowshare. Plowshare was an effort to develop techniques and nuclear devices for non-military construction purposes. AEC was opposed by both local Alaskan population, indigenous communities, and the scientists whose work would be directed towards the project. This was sufficient to discourage AEC from proceeding, and the failure of Chariot can be pinned on AEC's reluctance to cooperate with public interests and willingness to falsify information. AEC's mismanagement of project scope translated into another needlessly failed program. Interestingly, we have already seen this assessment of AEC come up before. There were concerns that AEC would overfund Orion long before the test flights had proven the concept viable. It's worth mentioning that ARPA, another newly founded specialized government agency, did not even keep written records of many of its projects in this period, so AEC's behavior, put into context, is less surprising. In the decade or so following the agency's formation, AEC may have had accountability issues in its involvement with federal projects. While there were glaring mistakes made by the agency in this period, we should not think of AEC as blundering and evil. The organization had limited resources, wider responsibility, and their leadership often had conflicting objectives. They failed to scale their scientists' ambitious proposals to something testable on multiple occasions. Project Chariot and perhaps even Orion could have benefited from a focus on scaled-down testing, but the emphasis was rarely placed on scalable tests. Building NPP vehicles today will require a realistic promise of immediate benefit to governments, economies, and science with the least financial, human, and ecological risk. Let's consider the ways we can fulfill these requirements while also responsibly handling the problem of nuclear proliferation and public opinion. As mentioned earlier, access to most nuclear technology and devices has historically existed in a unique hierarchy which serves specific national agendas. Will a NPP needing thousands of nuclear devices be incongruous with the goal of shrinking our stockpiles of weapons? Will we have to employ weapon production infrastructure and organization in the production of nuclear pulse devices? We'll try to answer these questions, but first we need to briefly assess some of the obstacles nuclear non-proliferation faces in this context. The original cost in materials, energy, and funds to build the strategic weapons existing today were an investment. Nuclear de-armament efforts struggle within this reality. The economic disadvantage of breaking down nukes and support infrastructure has led to consistent retention of nuclear arsenals. Nuclear de-armament efforts may at times appear to be going well, but the nature of this issue is complex. Many strategic weapons have been disassembled in recent de-armament treaties only to have their material later reused in deployment of new, if not identical, weapons. We cannot simply get rid of the nuclear material we generate when de-arming our arsenals. We must apply it towards useful application. NPP represents an opportunity to cash in on the investment of established strategic arms stockpiles. Being expensive to maintain, strategic weapons lose value every day, while their enriched elements appreciate in value by this process of conversion into pulse devices. The fact these resources are already national assets means the scale of their production can be closely regulated so that domestic demand for enriched material does not fluctuate if such is a concern. Nuclear pulse devices are low yield and are not viable for military use. But these assets will not be permissible to be owned and manufactured by private entities for some unforeseeable amount of time. When a nuclear pulse ground launch occurs, global cooperation will be needed for safety. Of the discussed concepts of external nuclear pulse propulsion systems, 4 stand out as being the most viable in short-term scenarios. The first is the Orion concept, whose mechanisms should already be familiar. The second is known as Daedalus. However, the vehicle bearing the namesake Daedalus is an interplanetary vehicle, and this scope is not relevant to our discussion today, but we will discuss its systems in a scaled-down context later. The third is Medusa, a concept with origins adjacent to Orion. It and our fourth example were first published in a 1958 memo titled The Bolo and the Squid by Freeman Dyson, a document which surprisingly remains classified to this day. Medusa is a simple design, using rotation to deploy flattened steel ribbons which absorb momentum from nuclear pulses. The fourth is the brainchild of John Dale Solom, another scientist who worked at Los Alamos. People have begun to refer to this design as Medusa as well, but I will note this design by Dr. Solom was an entirely new concept, and while it may have been inspired by Dyson's Medusa, it operates on different principles. Solom's spinnaker design used a large canopy of polyethylene material to absorb a nuclear pulse's momentum, unwinding a tether and propelling the spacecraft in this exchange of momentum. Some of these ideas are especially attractive today since they could be built using very limited materials and budgets, entirely in space perhaps. A paper published in the Journal of the British Interplanetary Society by Solom discusses how water and lunar regolith could be used to build nuclear pulse devices in lunar orbit, potentially solving the problem of creating devices with proper propellant properties in space. The article outlines using a NPP vehicle based on Medusa built in lunar orbit and driven by pulse devices assembled in space from local resources. This option is highly attractive since it could be carried out without severe political concerns inherent to surface or orbital assembly of nuclear materials. All of these designs, and Orion as well, share the shortcoming of consuming amounts of nuclear material that do not add up to a trivial cost. The nuclear material is the most expensive part of an NPP system, and this is a problem which will never be truly minimized. The aforementioned interstellar Daedalus design is a concept working from studies conducted under the Air Force Office of Scientific Research. In the 1972 report, Thermonuclear Microbomb Rocket Propulsion, a sound argument is made for using beams of electrons traveling at relativistic velocities to detonate very small nuclear pellets. These methods allow for more efficient energy output since they utilize helium-3 deuterium fusion, providing only charged products, while the less efficient tritium-deuterium fusion process yields only 20% of its energy as charged products. Modern nuclear pulse technology as it exists in laboratory research exclusively surrounds fusing small particles of nuclear material with a beam of particles, electrons, pulsed lasers, or a projectile slug. Very small thermonuclear detonations release much more energy for mass than discrete fission-based devices can achieve. This highly efficient approach solves many of the inherent issues with legacy NPP designs, notably the propellant cost and mass. SIRIUS is a facility built by the UK's Science and Technology Facilities Council UKRI, based at the ISIS Neutron and Muon Accelerator in Oxfordshire, and provides the needed tools to establish microfission experiments proving Daedalus' miniature practicality. Available information on these devices is extremely limited on the internet, with the original proposal being the only outline we have to appraise the facility's current capabilities. While the SIRIUS facility can conduct proof-of-concept testing, a much more expansive facility would be needed to test the full-size fusion pellets a Daedalus would carry, even a miniature Daedalus. The common problem with these specific NPP technologies is, while they are completely feasible and discussed seriously, they still hinge on systems that have never seen a real-world application to prove their concepts. Triggering fusion pellets of this design with a beam of electrons or photons is probably not prohibitively expensive using modern technology. The potential hurdles for these more recent nuclear propulsion systems make them less attractive than the established nuclear pulse methods used by Orion. This debacle illustrates how static research into fission systems has become due to political issues, and this situation suggests a return to continuing our research where we abandoned it might be a better option than leaping forward to revolutionary new applications. John Greenwald, a well-known proponent for freedom of information, has made broad requests to the NSA for any unclassified information maintained by intelligence agencies today on Project Orion. This signifies Greenwald is making a request to make public, under the Freedom of Information Act, any information resources related to Project Orion which had not been provided in previous requests. However, this request was recently met with a no-record disposition, implying any information referenced in documents we do not have today, which are numerous, is still classified. Very few technologies have garnered this level of secrecy by US intelligence, and it's worth noting these are primers, planning, and concept documents, not technical reports. We are running out of first-hand sources for these civilization-changing technologies. The most important science achieved during the Manhattan Project and in nuclear testing conducted after will never be repeated again. Although computer simulation stands in for nuclear testing today, very few people available as public resources exist who are experts on constructing nuclear devices. Recognize that many figures in our governments and agencies are pushing for nuclear technology in space, and that supporting these political processes will be vital to bringing new attention to past and future technologies of great promise.